Hey there, car enthusiasts. It's Jay Leno, and today we're talking about something that's been buzzing in the automotive world: electric vehicles. These days, you can't turn a corner without seeing a Tesla, Chevy Bolt, or some other sleek EV cruising down the street. Behind every great electric car is an even greater battery. These powerhouses are the unsung heroes of the EV revolution. They're what keep these cars running, and they're the key to making electric vehicles a real alternative to our gas-guzzling friends. These batteries are getting better every day, allowing cars to go further, charge faster, and perform better than ever before. But here's the thing. As amazing as these batteries are, they're not perfect. From range anxiety to charging times, from costs to environmental concerns, the road ahead for EV batteries isn't without its bumps. Let's pop the hood and take a closer look at what makes these EV batteries tick. At the heart of most electric vehicles today, you'll find lithium-ion batteries. These are the same type of batteries that power your smartphone or laptop, just on a much larger scale. These batteries work by moving lithium ions from the negative electrode to the positive electrode during discharge, and back when charging. The beauty of lithium-ion batteries is their high energy density. This means they can store a lot of energy in a relatively small space. They're lightweight, which is crucial for cars. They can be recharged many times without losing much capacity. But like any technology, lithium-ion batteries aren't without their drawbacks. They can be sensitive to extreme temperatures, which can affect performance. Now let's talk about something that keeps many potential EV buyers up at night: range anxiety. It's that nagging fear that you might run out of juice before you reach your destination. The range of electric vehicles has come a long way. When I first started seeing EVs on the road, you'd be lucky to get 100 miles on a single charge. Now we're seeing cars that can go 300, even 400 miles on a single charge. But even with these improvements, range anxiety persists. Part of the problem is that the range of an EV can vary quite a bit depending on factors like driving style, weather conditions, and terrain. Crank up the AC on a hot day or tackle some steep hills, and you'll see that range drop faster than you might expect. It's not like a gas car where you can just pull over and fill up in a few minutes if you're running low. Despite all the advances, batteries still can't match the energy density of gasoline. Improving energy density is one of the biggest challenges facing battery researchers today. Let's shift gears and talk about another big challenge: charging. With a gas car, you can pull up to any gas station, fill up in a few minutes, and be on your way. With an EV, it's not quite that simple. Charging takes time, and finding a place to charge can sometimes be a challenge. Even with the fastest chargers available today, it still takes about 30 minutes to an hour to charge most EVs to 80%. And if you're using a slower charger, like the ones many people have at home, it can take hours to fully charge a car. While the number of charging stations is growing, they're still not as ubiquitous as gas stations. This can make long trips in an EV a bit more challenging, requiring careful planning to ensure you can find charging stations along your route. The good news is that both of these issues are being addressed. Charging speeds are improving, with some new technologies promising to cut charging times down to just a few minutes. Section 5. Battery longevity, the ticking clock of performance. Now let's talk about something that's on the mind of every car owner: longevity. How long will that expensive battery pack last? It's a crucial question because the battery is the heart of an electric vehicle. The good news is that EV batteries are designed to last a long time. Most manufacturers warranty their batteries for 8 to 10 years or 100,000 miles. And in many cases, the batteries are outlasting these warranties. I've seen Tesla Model S cars with over 200,000 miles that still have 90% of their original battery capacity. But here's the thing: batteries do degrade over time. Every time you charge and discharge the battery, it loses a tiny bit of its capacity. This degradation is usually gradual, but it does add up over time. Factors like extreme temperatures, fast charging, and keeping the battery at very high or very low charge levels can speed up this degradation. As the battery loses capacity, the range of the vehicle decreases. Section 6. The price tag, high costs of EV battery production. Alright, let's talk money. One of the biggest hurdles facing electric vehicles is the cost, and a big chunk of that cost comes from the battery. These high-tech powerhouses don't come cheap, and that's reflected in the price tag of EVs. To give you an idea, The battery pack in a typical electric car can cost anywhere from $5,000 to $15,000. It's one of the main reasons why EVs tend to be more expensive than comparable gas-powered cars. So, why are these batteries so expensive? Well, it's a combination of factors. First, there's the cost of the raw materials. Lithium, cobalt, and nickel, key components in most EV batteries, aren't cheap. Then there's the manufacturing process, which is complex and requires specialized facilities. Section 7. Raw materials, sourcing challenges, and ethical concerns. Now let's dig a little deeper into where these batteries come from. It's not just about the technology. There are some serious challenges when it comes to sourcing the raw materials needed to make EV batteries. The key ingredients in most EV batteries are lithium, cobalt, nickel, and graphite. These materials aren't exactly abundant, and they're not evenly distributed around the world. Take lithium, for example. Most of the world's lithium comes from just a few countries, like Australia, Chile, and China. But the real controversy surrounds cobalt. More than 60% of the world's cobalt comes from the Democratic Republic of Congo, where there are serious concerns about working conditions and child labor in some mines. Many companies are now working to ensure their cobalt comes from responsible sources, but it remains a challenge. Then there's the environmental impact of mining these materials. Large-scale lithium extraction, for example, can use a lot of water and potentially harm local ecosystems. Section 8. Recycling roadblocks. Dealing with used EV batteries. Alright, let's talk about what happens when these batteries reach the end of their road. Recycling EV batteries is a critical challenge that the industry is grappling with. It's not just about disposing of old batteries, it's about recovering valuable materials and minimizing environmental impact. EV batteries are big, complex, and potentially hazardous if not handled properly. They can't just be tossed in the recycling bin like an old soda can. The recycling process is complex and energy-intensive. It involves breaking down the battery, separating the different materials, and then processing them for reuse. A used EV battery that's no longer suitable for powering a car might still have 70 to 80% of its original capacity. So instead of recycling these batteries right away, many are being repurposed for less demanding applications. However, even with repurposing, we'll eventually need to recycle these batteries on a massive scale. New recycling technologies are being developed that can recover more materials more efficiently. Section 9. Innovation on the horizon. Solid-state batteries and beyond. Now let's look ahead to what's coming down the pike. The world of battery technology is buzzing with innovation, and one of the most exciting developments is the solid-state battery. This could be a game-changer for electric vehicles. So, what's a solid-state battery? Well, unlike current lithium-ion batteries that use a liquid electrolyte, solid-state batteries use a solid electrolyte. Solid-state batteries promise higher energy density, faster charging times, longer lifespan, and improved safety. They could potentially double the range of electric vehicles while reducing the risk of fire. Sounds great, right? So why aren't we using them already? Well, there are still some hurdles to overcome. Manufacturing solid-state batteries at scale is challenging and expensive, but progress is being made. Companies like Toyota, Volkswagen, and several startups are pouring billions into solid-state battery research. The future of battery technology is wide open, and it's an exciting time to be in this field. Section 10. Alternative materials, exploring new frontiers. Let's shift gears and talk about some of the alternative materials that researchers are exploring for the next generation of batteries. One promising avenue is sodium-ion batteries. Sodium is much more abundant and cheaper than lithium, which could help bring down battery costs. Another interesting development is the use of silicon in battery anodes. Silicon can potentially store up to 10 times more energy than the graphite currently used in most lithium-ion batteries. Then there's the realm of organic batteries. These use organic compounds instead of metals in the electrodes. Some researchers are even looking at using materials derived from plants. The challenge, as always, is matching the performance of current batteries while bringing these new materials to market at a competitive price. Section 11. The road ahead, a brighter future for EV batteries. As we wrap up our journey through the world of EV batteries, I can't help but feel excited about the future. Sure, we've got some big challenges to overcome, but that's what makes this field so dynamic and interesting. The pace of innovation is breathtaking, and I truly believe we're on the cusp of some major breakthroughs. In the near term, we're likely to see continued improvements in current lithium-ion technology.